Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Socket Programming Part 1, in which we will program client and server processes using Internet Domain TCP sockets. Well dear students, if you have not seen the previous session, that is video lecture number 33 on Internet Networking with Linux, please see that first, in which I have discussed the TCP IP stack and the use of various services like Zinetd, Telnet, Eco, Daytime, SSH, and so on. Well, this slide shows the agenda of today's session, and we have a lot to do today, so let's start playing. Okay, before proceeding, let us have a quick recap of client-server paradigm. Remember, a socket is an IPC tool that is used to communicate between related or unrelated processes executing on same or different machines in a local area network or maybe on the internet. A process or application that waits for incoming communication requests is called a server process. There may be a lot of server processes running on this server machine, as shown over here, each listening on a dedicated port. There are a lot of services. The first part of the list, like Eco, Discard, Daytime, Charge, and Telnet and Time, they normally run under the control of Zinetd, while these remaining like FTP, SSH, DNS, HTTP, and so on, they normally run in the standalone mode. Okay, let's talk about the client machine as well. A process or application that initiates a request to a server process is called a client process. And there can be a lot of client processes running on this client machine. For example, in the last session we have seen the Netcat, Telnet, SSH, and you all have used the web browser, which is a client program for a web server running on a server machine. Well, dear students, when a server process receives a client request, it performs the necessary computation and returns the result to the client. And remember, a machine is identified by its IP address and the process is listening on a specific port. Well, as far as this connectivity is concerned, these clients and server programs can have short connections, or maybe they have long connections. For services like Time and Eco, the interaction between the client and server is limited to one request and one response. So they are short connections. And for services like Telnet, SSH, HTTP, FTP, the interaction between the client and server continues until the client sends some sort of a quit message to the server. So we call them long connections. Similarly, the servers can be stateful or stateless. A stateful server is a server that remembers client data or the client state from one request to the other. For a stateful server, the client can send less data with each request and is simpler. On the contrary, a stateless server keeps no state information. And this statelessness improves reliability at the cost of longer request and slower performance. And finally, the servers can be iterative or concurrent, and they both can be connection oriented or connectionless. Okay, so to fully understand and do all these tasks, we need to start from one end. Let us do that, and let me start with the definition of a socket. So a socket is a communication endpoint to which an application can write data to be sent to the underlying network, and from which an application can read data. The process or application can be related or unrelated and may be executing on same or different machines. We have different APIs available for different platforms. For Unix, we have the Socket API that is developed by University of California, Berkeley, and is used in BSD Unix. The other flavor of API is X-Open Transport Interface, also famously known as the TLI or Transport Layer Interface, which is developed by AT&T and used in System 5 Unix. We will be using the socket API. Dear students, we will be discussing two types of sockets, the internet domain and the Unix domain sockets in our future sessions. And every socket implementation provides at least two types. One is the TCP, also known as the stream socket, and the other is the UDP, also known as the datagram socket. In today's session, we will be talking about the internet domain stream sockets. And the others I will inshallah discuss in the next sessions. So let's talk about the stream sockets. Stream sockets provide a reliable, full duplex, stream-oriented communication channel. Stream sockets are used to communicate between only two specific processes and are described as connection-oriented. They do not support broadcasting and multicasting. These are some of the features that I have mentioned over here. Full duplex means data can be transmitted in both directions. Stream-oriented means, as with pipes, there is no concept of message boundaries in TCP sockets. As far as reliability is concerned, reliability is achieved by sequence numbering and acknowledgements so that the data can be reconstructed in order, regardless of any fragmentation, disordering, or retransmission of lost packets. Error detection is using checksum is done to ensure correctness of data. And this flow control using sliding window ensures that the sender do not send data too fast for the receiver to receive and process it reliably. In case if the receiving host buffer fills up, the next acknowledgement contains a 0 in the window size to stop transfer and allow the data in the buffer to be processed. This congestion control is also a feature of stream sockets. Congestion control algorithms aims to prevent a TCP connection from overutilizing the network. It uses a sender side congestion window and a receiver side advertised window. TCP cannot send more data than the congestion window allows. Similarly, TCP cannot receive more data than the advertised window allows. Whenever the network experiences heavy traffic conditions, the congestion window becomes small, and when the network is lightly loaded, the congestion window becomes large. Dear students, you have taken this course, the computer networks, in the undergrad. You must have studied different algorithms for congestion control, like slow start and maybe fast retransmit. For strong theoretical and conceptual grounds on these concepts, I will strongly recommend that you go through the main pages of TCP from section 7, and I will also like you to go through the RFCs, different RFCs, for example the RFC of the 793 for transmission control protocol, 768 for user datagram protocol developed by DARPA, and 791 for the internet protocol. And do go through these. Let me show you the internet header format. You must have seen this in your undergrad course. Let me fall back to over here. Do see the man page of UDP and do read it. Do read the man page of IP as well, and start with the RFC 791, and you can see the latest RFC as well. Okay, let's fall back over here. Okay, now it's time to talk about programming. Let us see the sequence of system calls that gets called behind the curtain when a client and a server program communicates. And let me describe the sequence of these calls with analogy of a telephone system. Right, dear students, the server makes the socket system call to create a socket, and it is equivalent to installing a telephone set. The server then calls bind system call to bind the socket to an IP address and an appropriate port number, and this step is equivalent to having a known or public telephone number. Then we have the listen call. This listen system call notifies the kernel of the server's willingness to accept incoming connections, and this step is equivalent to waiting for incoming calls on the phone. And finally, the server program logs on accept system call until a connection request arrives. Let's now talk a bit about the client sequence of calls. The client also makes the socket system call to create a socket, and it is also equivalent of installing a telephone set. It is assumed that the client knows the address of the server, so it calls connect. It is equivalent of dialing the telephone number. The connection is established using the famous three-way handshake. On the server side, a brand new socket is created called the data socket. And now the data can be transmitted in both directions between the client and the server, analogous to the two-way telephone conversation. Both the client and the server communicate via this data socket, while the master socket continues listening for new connections. We can use the conventional read and write system calls, or you can use socket-specific system calls like send and require for TCP sockets, and send to and require for UDP sockets. Anyways, once the client is done, it calls close on its socket, which sends an end of file notification to the read call on the server side. The connection terminates, and the server also closes the data socket and moves back to accept system call to accept the next incoming connection on the master socket. So this is how the sequence of calls goes. I hope it makes sense and it's clear to you. Let me use another illustration to explain that in case of a TCP server, there are two sockets, one using which the connection is established and the other on which send and receive operations are carried out. So let's suppose this is a server and this is the socket, normally known as the master socket, created using the socket system call. We have a client also makes a socket call to create a socket, and this connection operation is carried out between the client socket and the master socket on the server. The server creates a data socket, and this is the data socket on which all the data transfer is going to be carried out, and the master socket of the server is again free and listening for a new connection from another client. And of course, this is a typo, this is not client 1, this is client 2. Anyway, so once the client 2 connects with the server, it also creates another data socket, and there you go. So on the server side, you have one additional socket that is listening for the incoming connections, and we have the data sockets, one for each client, on which the client communicates with the server. I hope the concept is clear. Well, this slide shows a pseudocode of sequence of system calls for TCP or stream sockets for server program as well as for the client program. And let us understand the three-way handshake with the help of this illustration. Well, the master socket on the server side is in the listen state. When the client calls connect, the TCP IP protocol sends a SYN packet to the server. After this, the master socket on the server side is in SYN received state, while the socket on the client side is in SYN sent state. The TCP IP protocol on the server side responds with a SYN ACK packet, meaning that I have received it. So being a client, when you receive a SYN ACK packet, you know that the server has got the packet. But till now, the server doesn't know that the client has received the packet. So the client also sends the ACK packet, acknowledgement packet, and once the server receives it, both parties are now sure that the packets are received. Meanwhile, on the server side, accept returns a new socket descriptor to be used for data transfer with the client. Now the data socket on the server side and the only socket on the client side are set to be in established state, and reading and writing is done on these sockets. Well, dear students, once the data transfer is complete, the connection termination takes place, and let me describe that as well. It is famously known as the four-way connection termination. The client process calls close first, and we say that client side performs the active close. The TCP/IP protocol sends a FIN packet to the server. The server process, which is blocked on reading, receives the FIN packet and performs a passive close. The server side sends an acknowledgement packet in response to the client's FIN packet. The server also sends a FIN packet to the client, and in response the client also sends back an ACK packet, and the server closes the data socket. After some time, the client also closes its socket. So finally, both the sockets are closed and the connection is terminated. Fine, let us see the proof of these concepts using different tools. And before I move on to the terminal, this is the lab setup, which is the same as discussed in the previous session. And today I will be working on Kali, having the IP of 192.168.100.21 and Ubuntu server running on 192.168.100.20 or 20. So let's move on to Ubuntu server first. Who am I? I am root. If config, and you can see the IP address is 192.168.100.20. Let me check the status of ZynetD first. systemctl status ZynetD, and it is not running. So let us run this service and let's check the status again. So it is running. Fine. Let me use netstat and check out the services running under ZynetD. Okay, so that is great. We have a process listing on 37 for time, port number 7 for echo, port number 9 for discard, 13 for daytime, 19 for chargen, and 23 for telnet. Okay, so we have seen this in the previous session as well. Let us access these services from the Kali machine. Who am I? I am Arif, and right now I am on. Okay, let me do sudo for if config. The IP is 192.168.100.21, and let me use netcat, which is a Unix utility used to read and write data across network connections using TCP as well as UDP. Let me connect to the echo server running on 192.168.100.20, which is the IP of Ubuntu server at port 7, and by default NC goes with the TCP connection. Let me write down learning is fun with Arif, and it echoed back. Let me check out the status of the ports. Let me move on to this and use netstat. Okay, and you can see we have this established connection, Kali machine and Ubuntu server. On Kali machine I am using the port number 37616, while on the Ubuntu server we have 7. So that is great. And since this is a client machine, so you have only one socket, and if I move on to the server machine and do a netstat, let me grab 7 you can see we have two ports. One port is one established connection at port 7 with the Kali machine at port 37616, and you still have a process listening out on port 7 on this Ubuntu server machine. That is great. So there are two sockets, data socket and the master socket. Let's move on to the Kali again and control this and close this connection. If I check out again, and you see right now this is in a timed wait state. So remember, once you close the socket, it may take a bit of time, maybe from 1 minute to 5 minutes to come out of the time wait state. Soon it will come out of this state. Anyway, you fall back over here and use strace now to just check out the sequence of system calls that NC use. Oops, that's great. Fine. Note the socket call. I will just highlight the calls of our interest, and you know what strace is. Just a simple debugger, tracing of the system calls. Note this socket call, which creates a stream socket and returns file descriptor 3. 0, 1, 2 are of course for std in, std out, and std error. Okay, then you can see this connect call. Let me highlight it. This connect call is passed the socket descriptor, which is 3, and then it is called the address of the Ubuntu server, the family, the port number, and the IP address, and this returns 0. That means success. Right now it is waiting on the keyboard to give the input. Remember, this select call allows the program to monitor multiple file descriptors, waiting until one or more of the file descriptors become ready for I/O without blocking. The arguments to select are the first argument is the highest number file descriptor in any of these three descriptor sets. This is the read descriptor set, and this is the write descriptor set, and this is the exception descriptor set, and this can be the timeout argument. And right now we are just interested in the read descriptor sets. Let me enter something. Learning is done with Arif. Okay, so after I have given the input, you can see the read system call first. That is, I have read from std in, then write system call. This client program has written to the socket descriptor, that is 3. Then is the select again, that is it is again blocked on these descriptors, and once the select is successful, it has read it from descriptor 3, which is in this set. And finally, it has used the write system call to display that content on std out, and this is the content that is displayed. I hope the concept is clear. Let me quit. Okay, let me clear screen. Let us dig a bit more deeper and run Wireshark. Wireshark is a packet sniffing tool. I have it over here. Let me close it. Okay, so I have run the Wireshark, the packet sniffing tool, and let me fall back over here and use NC again, 192.168.100.7, 100.20, the IP of Ubuntu server, and port 7. Let me enter PUCIT, and you see it has echoed back. Let me press Ctrl C, and let me see the activities on Ubuntu server on this packet sniffing tool, Wireshark. Well, there are three panes over here. Let me filter the types for TCP only, and these are the three panes. The first pane in which my arrow is there displays one line summary for each packet captured: the time, the source IP, destination IP, port length, and the information. And once you select a packet over here, this second window is the packet header window. You can see the details of the selected packet. For example, if I select this request packet, and you can see over here, you can see all the headers, and if I see this, and you can see the data. You can see the data over here. And once you select something in the packet header window, in this third pane we have the packet content window, which displays the contents of the packet, captured packet, in hex as well as in ASCII format, and you can see PUCIT over here. Moreover, you can see the Ethernet packet contains the source and the destination hardware address. The IP packet contains the source and the destination IP address, and over here we have the port numbers as well, and you can see details. Anyway, let me show you the TCP three-way handshake. In the very beginning, you can see the three-way TCP handshake: the SYN packet, the SYN ACK, and the ACK. The SYN is sent from Kali to Ubuntu server. The SYN ACK is sent from server to Kali, and then finally from Kali to server the ACK has gone. And if we go at the end, we have the four-way connection termination. From the client to server we have the FIN-ACK packet, and from server to client we have the FIN-ACK packet, and finally from client to server we have the ACK packet. Fine, and we have this is the request. You can see the request PUCIT, and this is the response, again PUCIT. Let me show you one more thing. And for that, let me start recapturing the packets in Wireshark. Let me stop it and let me start it again. I don't need to save it. Okay. Fine. Let me run this again, and let me give it lot of data. And let me open a file at C passwd, and let me copy the contents of this file. Okay, enough. Okay, so that is it. Let me copy these contents and let me paste them over here, and let me press enter. Okay, now let me fall back to the Wireshark and show you some important things. You can see we have now the data sent in multiple requests, multiple packets. Some data is sent here, 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 here. So a lot of requests and a lot of responses. The point to be noted is that the second packet is sent only after the server has received the acknowledgement. So in case if you are sending a lot of data, remember whenever you are reading data from a TCP socket, you should always read in a loop until the desired amount of data has been received. This is important. Okay, so far so good. Let me stop this capturing. Come up over here. Let me control C this. Okay. So that is great. Well, let's fall back to the slides. Fine. Now we need to write down our own echo and daytime client and other clients, and for that we need to study a bit of the arguments to the system calls which we have just seen. And the first call I'm going to discuss is the socket call. The socket call is passed 3 arguments. The first is the domain, which can be AF_INET, for today's session, that is IPv4, that uses 32-bit IP address and 16-bit port number. The second is the type, and a type will be for today's session SOC stream. If you are interested in UDP, you can write down SOC dgram. And as far as the protocol is concerned, we will preferably place a 0 over here and let the TCP IP choose the correct protocol based on this type. Dear students, once the socket call is a success, you get a file descriptor, and which is pointing to a data structure of socket, and this socket data structure contains several pieces of information. Some important are shown over here. The family and the service are populated after the socket call, and we have the local IP and local port, and the remote IP and the remote port. Well, remember, dear students, when the local address is stored in this data structure, we say that the socket is half associated. And when both the local as well as the remote addresses are stored in this data structure, we say that the socket is fully associated. Well, let's see how the addresses, these two addresses are populated in this socket data structure. If this is a socket on the client side, the remote IP and remote port, these addresses are populated via the connect call, and the local endpoint addresses are automatically populated by the TCP IP software when the client calls connect. And if this is a server side socket, the local endpoint addresses are populated by bind system call, and the remote endpoint addresses are populated once the accept call returns. Okay, fine. Well, after creating a socket, the client calls connect system call, and the first argument to connect call is the socket descriptor. The second is the address of the server, that is appropriate IP address and port number on which the server is listening, and the type is of SOC ADDR structure, and I will talk about this in upcoming slides. The connect performs these 4 tasks. First of all, it ensures that the specific socket descriptor is valid and it is not already connected. It fills in the remote endpoint address in the client socket from the second argument, and automatically chooses a local endpoint address by calling the TCP IP software. And finally, it initiates the 3-way handshake, as we have seen. Okay, so these are the address structure. Remember, dear students, this is the generic address structure SOC ADDR, and this is the actual internet socket address structure which we are going to use. These are the 4 members of the structure: SYN family, SYN port, SYN address, and SYN 0. These are the padding. SYN family is normally AF/INET, SYN port is the port number. Let me show you this on the next slide. Yes, over here. This slide shows how we are going to populate the address structure before calling connect system call. Okay, so we will create the SOC ADDR in type of structure, and this SYN family is AF/INET, and SYN port is 54154. This H2NS, host to network short function, is used to convert this 16-bit port number from host byte order to network byte order. Remember, dear students, our 8086 machines are little endian, while all the data on the network is big endian, which is normally called the network byte order. Similarly, while receiving integer data from the network, do remember to convert it to the host byte order using functions like this: host to network short or network to host short. So while sending you use H2NS, and while receiving you use N2HS. Okay, over here this function INET A to N is used to convert IPv4 or IPv6 internet address from this dotted decimal C string format to a 32-bit binary network byte order value. So remember, you need to use this. And this is the loopback address. You can mention the address of Ubuntu server over here. Well, this memset is used to fill up the padding area with null bytes, and finally we call connect, and always cast the address to the generic address structure SOC ADDR. This is done because the address structure of all families need to be passed to calls like bind, accept, connect, send to, and require from. In 1982, there was no concept of white pointer, so the designer defined a generic socket address structure. So remember, do not forget to cast your address to this generic address structure. Well, this slide shows the concept of little endian and big endian. Remember, the network ordering is always big endian, and our machines are mostly little endian. And these are the byte ordering functions. You can change from host to network and network to host for short as well as for long values. And this is the inet ADDR. This is the old version. It is always better to use inet A to N, which works fine for IPv4 as well as for IPv6. And the famous read and write system call, you know about them. Okay, send is quite similar to write system call if we place a 0 in the fourth argument, that is this flags. And to send out of band data, you can mention msg_oob flag as this fourth argument. The receiver will get the signal sig urge on receipt of this data. Similarly, the requv call is quite similar to the read system call. If we place again a 0 over here in the fourth argument, to receive out of band data, you can mention message oob, msg_oob flag, and on receipt signal sig urge will be generated telling you that there is an urgent data, so you can read it quickly. Remember, if requv system call returns 0, it means that the remote side has closed the connection on you. Well, as I have already said, the data from a TCP socket should always be read in a loop until the desired amount of data has been received. Consider a scenario in which the server process has sent 128 bytes of data to client process in 32 bytes chunk using 4 write system calls. On the client side, the client may receive all 128 bytes of data in one read call or maybe in multiple read calls. So use this code snippet whenever reading a TCP socket. Perform your read in a loop to ensure that you have read the entire data. Okay, dear students, as we close file descriptors, we also close socket descriptors when we are done using the socket. Remember, the remote side can tell if this happens in one of the two ways. If the remote side calls read, it will return 0, and if the remote side calls write, it will receive sig pipe. For socket descriptors, you just want to change the usability of the descriptor, you can call shutdown. And the second argument to shutdown is how can be shut RD, shut WR, or shut RDWR. If you just want to close the reading on the socket, you use this. For writing, closing the writes only, you use this. And if you do not want that any send or receive should be allowed, then you use shut RDWR. Remember, shutdown, do not just freeze the data structure associated with the FD. For that, you still have to call close. Okay, dear students, now we are well equipped. I think we are well equipped to write down our own client programs using internet domain TCP sockets. So let us move on to the Kali terminal and see a sample code that I have written to save time, that is TCP Eco Client. Well, this program connects to the Eco service running on the Ubuntu server having IP 192.168.100.20 at port 7, I think. If we see the code, the first call is of course the socket call with 3 arguments. The domain is PFINet, it can be AFINet. The type is sock stream, and the protocol is kept 0 to let the kernel choose the correct protocol based on the socket type. And before I call connect, over here I am creating the socket data structure for remote IP and port, and let the local IP and port be selected by the OS itself. You can see this is the IP of the Ubuntu server machine. We have discussed these four members of SOC ADDR on the slides. So let's move on to the third step, that is the connect call. We call connect, and after we are done with the three-way handshake, this is our protocol. And the protocol says that you read from std in, you write to the socket descriptor, you read from the socket descriptor, and you write to std out. And this is what we have just seen when we have used strace on netcat. And this is repeatedly done in a while one loop. Remember, dear students, for keeping my code simple, I have not done any error handling, and moreover I have not performed reading in a loop as I have discussed. Let me save and quit, and let me compile this program, echo client.c. Okay, so before I run it, let me move on to the Ubuntu server, and let me use netstat -ant, and let me grep 7. You can see there is just one entry for port 7, and that is in listening state. Let's come back over here, let me run it. Learning is fun with Arif, and it is echoed back successfully. And if I come back over here, you can see the established connection over here. The local machine is 192.168.100.20, while the remote is 192.168.100.21. That is great. Let me close this, come back over here, check it out. You cannot see the established connection anymore. Okay, that is great. Let's write down, let's see the code of another client, that is TCP daytime, that accesses the daytime service running on Ubuntu server, gets the ASCII daytime string and display it on std out. Okay, so here again we are creating the socket. We are populating the address with, of course, the IP of the Ubuntu server, and the port number is 13 on which the daytime service runs. The client calls connect, and the important point to be noted over here is that the client sends no data to the daytime server. It just read, which is not the case as with the echo client. The daytime server simply sends the date on connection establishment, so you don't need to actually send any data. The client just read the socket and display the time on std out over here. That's great. Let's compile it. gcc tcp daytime client.c, let me run it, /a.out. So that is great. That is great. Okay, now I think we all know how to write down a client program. You can write down more client program of your own. Let us move to the slides and see some more system calls that will enable us to write a internet domain TCP server of our own. We need to learn 3 more calls, and the first is the bind. The server program first makes the socket system call to create a socket, and then use bind call to bind the socket descriptor with the address passed as the second argument over here. And the third argument is, of course, the size of the address structure. Then we have the listen call, and the listen call actually requests the kernel to listen on that specific socket mentioned in the first argument, and this is the size of the queue on which the master socket can wait for this much number of connections in a queue. So normally the size of this is normally 10. And then we have the famous accept call, which is used by the server process, and it returns a new socket descriptor to be used for the client for sending and receiving data. This first argument is the sockFT that we have created using the socket call, and this is an empty pointer which will be populated automatically once accept returns. This is just like the caller ID you get on your telephone number, and in this address structure you will get the IP address and port number of the client process. Okay, so let's move and see the proof of this concept, and I have TCP echo server for this. TCP echo server.c. Well, this is a server program that we will execute on Ubuntu server. So it will listen on some ephemeral port, will wait for incoming connections, read the data from the client, and will send it back as such. Okay, let's see the steps quickly. Well, the step one is same. We have created the socket. Remember, we have to create two socket ADDR in structure, one for the server address and the other for the client address. We have two sockets, one for the master socket or server socket, and the other is the data socket or the client socket. And the first thing I have done is created the socket. This is the master socket on the server side. Then I have created a address structure containing the server IP address, because I want to bind this socket with the server IP and port. And the server IP is of course 192.168.100.20. that is the IP of Ubuntu server, and this is the ephemeral port 54154, safe to be used. And then I am calling the listen call, and the backlog or the queue size is 10, which I have declared above. And then I will print this message, server waiting for a client connection, and then this is the accept call. This will be a blocking call, and this accept call will block until a client connection will arrive. And finally, this is a code that is reading from this socket descriptor, this client socket descriptor, and writing it back. So I'm reading from this data socket, and I'm writing to this data socket in this loop until read returns 0. So that's fine. Let me save and quit. Let me compile GCC TCP echo server.c. Let me compile it with the name of TCP echo server. Remember, right now I'm on the Kali machine, and I want this to run on Ubuntu server. So let me use SCP secure copy. Let me copy this program TCP echo server to the machine having the IP of 192.168.100.20, and let me copy it in the home directory of root. So most probably it says, okay, I have given the wrong IP address, that is 192.168.100.20, asking me for password. Okay, I'm not going to tell you. It has successfully copied this file over there. Let me go over there, and right now I'm root in my home directory. Let me ls, the program is there. Let me run this program, TCP echo server, and it is running. Oh, that's great. Let me fall back over here, and Let me use a client now. I can use NC, but let me use TCP Eco Client. Eco Client. And in this TCP Eco Client, the port number to be used now should be 54154. Let me correct this, 54154. The IP is same, but the port should be 54154. Let me save and exit. Let me do gcc tcp eco client.c and let me run it. Okay, so I have not sent any data. You can see the client connection established message. Learning is fun with Arif. Echoed back. It's working fine. Okay, bye. And Control C. And you see the client connection terminated and server is again waiting for another client connection. Let me run it again. This is fun. And you see the client connection is again established. And if I press Control C, so it is terminated, but the server is still running. Let me press Control C and quit this server. Well, dear students, let me now discuss some important lookup functions. Sometimes the client do not know the IP address of the server. Rather, the client know the domain name only. So there has to be a function to which we pass a domain name and it returns us the respective IP. And the function name is gethostbyname. Okay. So this function takes the domain name as its only argument and return a pointer to the host and structure that contains the host IP address and some other details. Let me show you the structure members, host and structure. Well, this is the structure, and this h underscore name, this contains the official name of the host, and this h underscore addr contains the IP address, and there are other details as well. Let's see an example code for this proof of concept. That is vim get host name.c. So a simple program receives a domain name via command line argument, pass it to get host by name function and display the host name and its corresponding IP address. Well, remember this inet n to a is a function that converts the IP address from binary network byte order to ASCII string. We have seen it before. Let me clear screen, compile this program, get host name.c, and let me run it on Ubuntu server, and the IP of the Ubuntu server is this, and let me run it on let's suppose Windows 10, and we know the IP of Windows 10 is 22. Well, these addresses came from the file etc host. We all have seen that file etc host in the previous session. This is a file on which we have mentioned the name and IP mappings of all the computers on this network. Let me run it on PUCIT.edu.pk, and let me run it on let's suppose arif.me. Well, these are the IP addresses that have been queried from the name server at my home router, and IP of that is inside resolve.conf 192.168.100.1, which is the address of my home router. So that is great. Let me talk about another lookup function. Well, dear students, sometimes the client do not know the port number on which the service is running. So there should be a lookup function to which we pass a service name and it returns us the corresponding port number on which that service runs. And the name of that function is getservbyname. Yes, this function takes two arguments. a service name and the protocol. On success, it returns a pointer to a servant structure that contains the port number. Let me go down and show you the structure as well. So this is the servant structure, and this is the port number in which we are interested. Let's see an example code, get port number.c. Again, a very simple program, receives a service name via command line argument, pass it to getservbyname function and display the service name, and also its corresponding port number. Remember, this N2HS, network to host short, is a function that converts a 16-bit port number from network byte order to the host byte order. Let us compile this program, get port number.c, and let me run it on, let's suppose, echo, and of course we know echo is 7. Let me run it on FTP, and FTP is 20, and if I run it on FTP data, that is 20, and for FTP it is 21. Let me check out for HTTP, and let me check out for HTTPS as well. And these information is extracted from the famous file that we talked before as well, and that is etc services. Let me grab HTTP from there like this, and you see port 80 for HTTP and 443 for HTTPS. That's great. Let's fall back to the slides again and see what is left for today's session. Okay, lookup functions, we have seen this and this. Okay, so let us conclude. Let me conclude today's session by giving you an assignment, and that is design and code of a TCP web server. This slide shows you an illustration that describes the general architecture of web application, just for brush up. A client machine runs the client program. In this scenario, it is a web browser, which is a program for retrieving, presenting, and traversing information resources on the World Wide Web. Some famous web browsers in no specific order are Google Chrome, Mozilla, Firefox, Safari, Microsoft Internet Explorer, Opera, Spartan, and so on. Dear students, when using a browser, we need to give the address of the resource that we want to get from the World Wide Web, and the general format is this. And in this address, there are 4 identifiers. The first is the protocol, which specifies the type of the vehicle to be used to fetch the resource. In our case, that is the web application case, this will be HTTP. Then we have the host name. This can be the IP as well, and the third is the port number. This is optional because for HTTP is 80, and then we have a slash, and after the slash we have the path that identifies the location and name of the file on the file system of the target machine. Well, dear students, the server machine runs the server program, and in this scenario it is a web server. And a web server is a program that uses the HTTP or maybe the HTTPS protocol listing on port 80 or 443 respectively for incoming HTTP request, and sends back HTTP response message to the client. So this is the basic concept. Some famous web server programs in no specific order are Apache, Microsoft Internet Information Server, Nginx, Lite, Jigsaw, and Oracle iPlanet web server, and there are others as well. Now, dear students, you all must be knowing that there are 2 types of web pages. The first are the static web documents whose contents do not change, and every static data request results in the same response. The static web documents are usually prepared in HTML, XML, or CSS, maybe AJAX or JSON. AJAX is asynchronous JavaScript and XML, and JSON is the abbreviation of JavaScript object notation. Other than the static documents, we have the dynamic documents, and when our dynamic data request comes, the web server runs an application program that may run on the same or maybe on different machine to generate the document and return it to the browser. The programs that generate such web documents are called server-side programs and are written in programming and scripting languages like CGI, PHP, Python, and so on. And these programs may also need to access some database to get the required data. Okay, now dear students, I think you have a fair idea of the architecture of a web application. Let us now understand the structure or contents of an HTTP request and HTTP response message, which you will be requiring in your assignment. Well, an HTTP request message is sent by HTTP client to HTTP server. It consists of a request line, few header lines, a blank line, and an optional body part. The request line contains space-separated 3 strings. This method defines the request type. Mostly it is get or post. This URL specifies the path to the requested source, and then we have the HTTP version. And we will see this soon on the terminal. As far as the HTTP response message is concerned, it is sent by HTTP server to HTTP client, and it consists of a status line, few header lines, a blank line, and an optional body part containing the requested data. Well, this status line contains space-separated 3 strings. The first is the HTTP version. The second is the status code, which is a 3-digit integer that defines the class of the response. Please see details of these status codes from Google. For example, 200 means OK. The code in 400 range indicates error. For example, 401 means unauthorized, and 404 means the page not found. And the third is the description of this status code. Okay, let me move on to the terminal and show you proof of this concept. And let me use curl for this. And curl is the command line tool to transfer data from or to a server. And let me use curl -v http let's suppose arif.me. Okay, so you can see this is the HTTP request, and this is the HTTP response from this part onward. So let me run the server. I think I have a server. Yes, I have a server. I've written the server. Let me run that server. GCC my web server.c. Okay, let me run it. Remember, this is the contents of the directory in which this web server will run, and I need to give it the port number. Let me give 54154 again, and let me do an ls first so that I can show you the listing of this. So this web server is running. Remember, these are the contents of the directory, and let me use netstat again to show you the status of the network sockets. And you can see this server is running and listing on 54154 on 192.168.100.21. Okay, so let us run curl on our own server now and try to understand. HTTP 192.168.100.21, and I need to mention the port because it is not standard, 54154, and let me press enter. Okay, so you see this is the HTTP request message containing the request line asking for the contents of the present working directory / empty line, and then we have the response. So the response message has the first line as the line containing the version of the HTTP, the status code, that is 200, and this is the body after the blank line. that contains, of course, the directory listing. Let me clear screen and let's give it a name of a file, hello.html. You see, this time in the response we have the contents of the HTML file. Okay, so let me move on to Safari. Open a terminal, write down the address http 192.168.100.21 this time, and the port number is 54154, and you see I have got the listing of that directory. And if I write down, let's suppose hello.html, this time this will be rendered and displayed properly because this is a browser. Let me ask for another file that is there. Let me check out the file. Let me call this hello.cgi file, which is an executable file. hello.cgi, and you see the file is executed. This is a script file containing commands like echo, date, and who am I. I think you all have a fair idea about the working of a web server and the contents of the HTTP request message and HTTP response message. Okay, so the web server which you are going to design, I think you are very much equipped to write it, because a web server is a program, you all know, that allows users on other computers to list directories, to read the contents of the file using cat, maybe run program using execlp. And the operation we need to code for a basic web server are, first of all, we need to set up the server, and we all know how to create a socket, put it in listen mode, and then accept a call. Then we need to read a request, and now I think I have given you a kickstart of about what a HTTP request look like. You should be able to read a request, and then you need to handle the request. For example, if you just get the / in the request message, you list the directories, you cat the files, you run programs using opendir, readdir, the loop2, exec. These are all calls you have done. And finally, of course, you need to send a reply in an appropriate HTTP response message. This illustration shows you the basic idea. The client uses a link, connect to the server accept the call, the client write the HTTP request, the server reads the HTTP request, process that request. If it is a directory, list it. If it is a regular file, cat it. If it is a, for example, .cgi file, it's run it. And if it is something else, the file doesn't exist, you create an error message. And then finally you send back the HTTP response. The client program read the reply, hang up, display the reply. And if it is an HTML file, it renders it. It is an image, draws it. It is sound file, play it and repeat. So this is a basic idea of a web server. I hope you will be able to write this. You don't need to write the client. You can use the curl for command line, and you can use any browser for GUI. Okay. I am tired. I think this is the longest session among all the system programming videos. In the next session, inshallah, we will talk about internet domain UDP sockets. And I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Happy learning, and Allah Hafiz.